This section is called ionization energy, and it is a concept you need to write that Born-Haber diagram. So what is an ionization energy? Well, it's an energy that you need to remove an electron. It's a positive and it is an endothermic process. Focus on this equation. What did I write? I wrote sodium, the element in the gas phase, going to form sodium, the cation, plus an electron. So ionization energy, this one is called the first one. It has a little subscript 1. It's the energy required to move the highest energy electron from a neutral gaseous atom. And so here we have its value. It is definitely endothermic, 496 kilojoules. So that's called a first ionization energy. There's something called a second ionization energy. Now, you will not have a neutral atom then. You already have a cation. And for that, I have used magnesium. I've shown how magnesium in the gas phase goes to form Mg plus an electron. It takes 738 kilojoules. If I try to remove another electron to make an Mg2 plus, it's going to take a lot more energy because I'm trying to take a negative particle away from a positive ion. Those are the key equations for ionization energy. On the next slide is a table, a very important table. Before I start talking about it, take a look and see if you can see some sort of trend. There's white, there's blue, there's something labeled inner shell electrons. Let's attack this. Sodium, the first one, is an S1 metal, and it has an ionization energy. What's happening when I'm trying to take away that next electron? Well, I'm trying to take that electron away from a neon core. It is a full shell. It does not want to give up an electron. And that's why these are labeled inner shell electrons. So that would be the values for sodium. If I go to magnesium, well, we know magnesium is a +2 ion. We know magnesium was formed by taking 2 electrons away from the magnesium atom to make magnesium 2+. Here I take 1, here I take another. But what happens with the third? I'm trying to take it out of a noble gas full shell configuration. If I look at aluminum as a +3, I go 1, 2, 3. Aluminum is an S2P1. Then all of a sudden, I have to go into the full shell. So this is insight. I would call it. It's not a fact. It's not memorization. It's using the facts that you have taught yourself in order to solve a new problem. Now, you may see any element on the periodic table on your exam. You should be able to think about what's the electron configuration and why is there such a big jump. Ionization energies, they really depend on the average distance of the electrons from the nucleus. So as we go down the periodic table, you notice the ionization energy is decreasing. I'll just take hydrogen versus cesium. Look at the huge difference. That's because we are seeing the value of N increase. We are seeing the atomic radius increase. And so that is the explanation we give for what's going on. Yes, there can be some things that are different, but in general, the trend is as you go down a group, you're going to see a decrease in ionization energy. What about when you go across the table? Well, we know that electrons are held more tightly as we move from left to right. And they're going to need more energy because also that effective nuclear charge, the ZEFF, is going to be greater. So we're going to see ionization energies increase across a period. The element in each period with the lowest ionization energy, that's going to be the alkali metal. The element with the highest, that's going to be the noble gas. Very easy to remember as you look at this chart and think that was on the intro for this chapter. What we have are a series of trends and we try to explain them. Okay, what do we have left? Well, we've got to talk to you about how can you make a cation. What are you doing to the electron configuration? I use lithium here that has a 2s1. I know lithium has a +1 charge, so goodbye to the electron with the orbital with the highest n. What about when you get to the transition metals? Remember, when we did a fill, we said 4s2, 3d6. But then we had to do it in terms of energy, and we said put the lowest n first, and that's what we're doing here. So if I have iron and I want to make an Fe2+, away go those 4s electrons. Now, Fe2+, it is not stable, okay? And think about when we talked about the egg, when we talked about the iron types of sulfide. Fe2+ has a 3d6. Let me draw it out. 1, 2, 3, 4, 5, 6. What we have here is a repulsion of the 2 electrons. So what it prefers to make is a 3d5. And as you noticed here, I said half-fill shell. I wanted to show you where does it come from. And a half-fill shell is a stable shell. Think of iron, Fe2O3. That is iron in the +3 oxidation state. We're going to talk about the cell in 1220. There's a very interesting thing with a ligand, but I can't go into it now, but it'll just make this make even more sense. There's going to be some things that don't fit the trend. One of them is beryllium versus boron. Beryllium has 2p electrons that are going to shield it, so it has a higher ionization energy. Boron has the electrons that'll be shielded. The other is nitrogen versus oxygen. Nitrogen is a half-fill shell. Oxygen has that 4th electron where there is going to be some repulsion and easier to remove. Finally, to wrap up this chapter, I've spent time with students in office hours. That's why I want to do it here in this video. When someone asks you to write an ionization energy equation, what you do is you take the element and you put it in the gaseous form. So here I have lead. I am going to say lead as a gas will undergo a process to form lead plus in the gaseous state plus an electron. What if someone said to write the first two? This one is the I1. How would I write the I2? I would take that Pb plus as a gas, and I would make Pb2 plus as a gas plus an electron. That would be my I2. Same thing with zirconium, but it says here 4th ionization. So for zirconium, I would begin with the +3 in the gas phase, and I would go to form zinc zirconium 4+ plus an electron. I better not forget the gas. So again, please practice. You can memorize the trends, that's good to know, but until you apply the trends, you really are only halfway there. So invest a little bit of time. This is not ultra hard. Take your time, ask some questions.